This is section 14.3, signal characteristics, wave number. So in this section, we're going to talk about the types of signals that we would see in IR spectroscopy, specifically the wave number and what they mean. So we talked a little bit about in the last lecture, 14.2, about how we assume that chemical bonds are springs and that atoms are on each side of the spring, and that these springs are governed by Hooke's law, which is a physical equation that's shown here. Essentially, what you can see is that what we're really concerned with is the force constant and the reduced mass of the two atoms. So the force constant is going to be kind of like how thick the spring is or how strong it is. And the reduced mass is an idea of how strong the bond is between, or not how strong the bond, but how large the two atoms are. So let's skip bond strength for now, and let's talk first about the reduced mass. So in reduced mass, the smaller atoms vibrate at a higher frequency, higher centimeters minus one, which means that as you go up in molecular weight from a C hydrogen bond to a C deuterium bond, already you have a big decrease in the observed frequency, which is V with the Inye guy on top of it. So even just from 1 to 2 changes the frequency a whole lot. Going from 1, which is the hydrogen, to oxygen changes the frequency even more to 1100, and going down to the chlorine, Cl, brings it all the way down to 700 wave numbers. So the reduced mass can have a huge effect on the frequency, because as you increase the reduced mass, it's in the denominator, so the frequency goes down. With the force constant, because it's in the numerator of this equation, let's bring it down here. With the force constant, because it's in the numerator of the equation here, the higher the number, the larger the frequency value, which means you have a higher wave number associated with that bond. So you have a very strong bond. You also have a high frequency. Now, before we move on, I don't just want to point to a function and try and get you to understand exactly what it means, because we have the internet, and let's show you a little bit about how this actually looks, because I found this tool online to kind of give you a little description or an idea, a conceptual idea of how this spring theory works. So here is the chemical bond we're talking about, anchored between two atoms. So if we make the spring thicker, that is, make the force constant higher, say this random value, the force that it takes to bend the spring is pretty high. It takes a lot of force. But as you reduce the strength of the bond, it takes a lot less force to bend the spring, which is why the frequency goes down. And you notice that as the spring constant goes down, the distance that it can travel goes way up. All right, so each of these now has its own characteristic frequency that the functional groups all correspond to. For instance, the carbon, nitrogen, hydrogen bonds are all around 3000 or higher, whereas if you have a carbon, oxygen, carbon, nitrogen bond, as we talked about before, they are much lower in frequency. And the stretching vibrations for double bonds are around 1700 for CC double bonds, whereas for single bonds, they're around 1000, or in this region here. From 1500 to 400, we call this the fingerprint region, and it's very difficult to determine what molecules are there. And from 1500 to 4000, we call this the characteristic or diagnostic region, where it's much easier to find the functional groups, because in organic chemistry, we're typically talking about hydrogen containing functional groups like these, or unsaturated functional groups, that is, molecules that have double or triple bonds, specifically C-double-O bonds. Okay, so as I alluded to, we're going to go back to the sheet of paper. As I alluded to, hybridization of the carbon can have a big effect on the stretch that we observe in IR spectroscopy, because with the hybridization, you have a big increase in the frequency of the carbon-hydrogen bond, for instance. So an sp3 carbon that's tetrahedral, it has a characteristic frequency of around 2900, whereas having a double bond on the carbon, an sp2, makes the carbon-hydrogen bond resonate at around 3100 wave numbers, and having an sp bond, a triple bonded carbon, hydrogen, gives you around 3300 centimeters or 33 inverse centimeter, or 3300 inverse centimeters, sorry. And you might be asking yourself, why is this the case? Well, it's this way because, again, of how far away the orbitals are from the nucleus of the atoms. So a p bond has very large orbitals, as we saw before, but as you get down to s, you also get much closer to the nucleus. And just like the spring analogy we were looking at earlier, the closer you are to the nucleus means that the force constant is going to be much higher because the bonds will be stronger. So as you get closer to S, more S character, you have a shorter bond, which means you have a stronger bond, which means you will have higher, oh, you can't see that, which means you will have higher frequency in the characteristic stretch number. Now, just some very good numbers to remember. Alkanes generally stretch below or around 3,000, alkenes above 3,000, and below 3,200, and alkynes greater than 3,200. One last thing I'd like to talk about is the influence of resonance on the characteristic shifts or stretches we would find. So let's take a look at a couple examples. These two being this propyl methyl ketone versus this, what would that be? That would be this 1,3-dione or dienone, this alpha beta unsaturated ketone. And if you take a look at these two molecules, they're very similar in the stretch for the CO bond, the C double bonded O, except the one in red has a stretch at 1680 instead of 1720. It has a lower frequency, which means the bond has been lengthened, the bond has been weakened. So why would that be? Well, if you look at the ketone, the only resonance structure you can draw is this one, the charge separated state. So the oxygen won't really be that often in the negatively charged state. However, with the red one, there are 3 resonance structures you can draw where the negatively charged oxygen, I left a negative charge out. The negatively charged oxygen, there we are, can be very happy in the charge separated state because it not only has the same one that we saw above for the blue, but also one where the double bond has helped to spread out some of that positive charge. So because there are more resonance structures that are valid and good, the oxygen will be more like a CO single bond. CO single bonds are longer than double bonds, and since they're longer, the bond is weaker, and that means that the characteristic frequency shifts down to 1680. This same trend holds true for esters. If you have an ester, which is a carbon with a double bonded oxygen and a single bonded oxygen, but some alkyl group, you have the same shift. Whoops, you can't see that. Okay, you have the same shift that occurs upon adding in resonance, this pi bond here. So just to recap, stronger bonds mean higher frequencies, and also shorter bonds mean higher frequencies. So if you have an increase in the stretch number, that means you have a shortening of the bond. If you have a decrease in the stretch number, that means you have a lengthening of the bond. And those lengthenings can have very real chemical meanings, especially depending on the types of resonance forms that you can draw with the molecules. This has been section 14.3.